this one term consists of that term and that. That term is equal to that. Okay. So now let's write everything together. Okay, this first term consists term 2 and that one. And term 2 is equal to that. So the second term, dv, and the integration is over st, that's that one. That term still remain, this term. So it's minus sigma ij delta epsilon ij dv. Okay, these two terms together is the first term here, and we still have that one, which is plus bi delta ui over with respect to tv dv equals 0. All right, now we have that. This is actually a weighted residual of the equilibrium strong form, and then with this process. During this process, as you can see, the differentiation is reduced on sigma. It increased on delta U. Okay? It also incorporates the natural boundary condition into it. Therefore, this is exactly the weak form that we are looking for. But at that point, we would like to rewrite it a little bit. We will write this term on the left side. We move the negative terms to one side, the positive term on the other side. Or, then we flip these two, okay? At the end, we want to write this on the left side, the other on the right. So we can write it as this sigma ij delta epsilon ij dv over volume is equal to body force dv, that is over v, plus traction boundary condition over st. This is the biggest, the most important thing of this lecture. That is the weak form of elasticity, which is almost ready for finite element implementation. Okay? If you look at the equation, actually it has some physical meaning to it. The left-hand side means the stress field times the corresponding string field, virtual string field, for every point and integrate over the whole volume. That means the strain energy of the body. Okay? What is that? That is the body force working, that does work on the virtual displacement. So that is work from the body force. That is traction, and again times displacement, and integrate over the whole traction boundary. That also means work from traction, because when you have body force, when the body moves, it will do work, right? And you have tractions. When the body moves, then the tractions will also do work. So this is total work from both the body forces and tractions. Of course, we know from the principle of work and potential energy, any work will be changed to elastic energy, which is a potential energy, like a spring. So this is like the energy absorbed inside a spring, because elasticity body acts like a spring. So that's spring energy, that's the work that's pushing the spring, which makes sense. That's exactly the principle of work and energy that we learn in dynamics course and other courses. Okay? And it turns out to be the weak form of elasticity that we can prove of it. But this is not it. Let's see what have we incorporated in the weak form. Remember? Okay, let me use this part. Hold here. Let's compare the strong form first. We have equilibrium, which is sigma ij comma j plus bi equals 0. We have kinematic or geometric relations. Epsilon ij is half ui comma j uj comma I. We have constitutive law that says sigma ij is equal to Cij KL epsilon KL. And then we have essential boundary conditions, that is ui equals no, unnatural boundary conditions that says sigma ij and j is equal to Ti, okay? And that's also no. And here, what have we incorporated into this? Refresh your memory about the derivation. We start with which one? Equilibrium. And change that to a weighted residual. So we effectively use this relationship. And along the way, what else have we used?
Kinematic.
Kinematic, right? Remember, I went through details that decompose that delta U comma J into this thing and say this is equal. So we use the kinematic. What else?
The natural boundary conditions.
We also use that. Very good. So this single equation incorporates three things here, which is nice. What we are left is this tool. So we still need to keep it. So we need to plus the constitutive law because it's not been used yet. Sigma ij, which is equal to Cij KL, epsilon KL. And then plus the essential boundary condition. Ui is equal to a no value. Okay? Therefore, if we carry these with that equation, this weak form of statement is fully equivalent to the strong form of statement. Okay, I think that's the way that conclude this lecture. So it's the second part of chapter 7 because it's a longer chapter. I think it's important to go through details. So that's why I spent 2 lectures on that. Okay, thank you.